Welcome back to our AI security journey. In Season 2, Episode 2 of the Vulnerability Chaining Masterclass, we dive into a lurking hazard that quietly turns AI output into a weapon. This episode, titled Improper Output Handling, the silent enabler of client-side attacks, explores how insecure rendering of a model's response can result in full-blown client-side code execution. It's part of our Vulnerability Chaining Masterclass series in the AI Security Edition. If you've just joined us, you might remember that Episode 1 unveiled the dangers of prompt injections, malicious inputs crafted to manipulate a model's behavior and leak sensitive information. If you haven't watched it yet, add it to your queue after the session. Now, let's unpack how trusting model output can crack open your browser. Before we get technical, a quick but important disclaimer. Everything demonstrated here is for educational and defensive purposes. Our aim is to raise AI security awareness. Always obtain proper authorization before testing systems. Follow ethical guidelines and practice responsible disclosure. As we dissect these vulnerabilities, remember, we're shining a light on weaknesses so the community can build stronger defenses, never to cause harm. Improper output handling occurs when an application accepts a language model's output without validation and directly renders it in downstream components. Unlike simple chat responses, LLMs can emit rich formats such as HTML, JavaScript, and Markdown. If the rendering layer treats that output as benign text, it can unknowingly execute untrusted code. This vulnerability matters because it opens doors to code execution risks. The model's output becomes a script running in the user's browser. It can lead to privilege escalation by stealing session cookies or performing actions on a user's behalf. And it bypasses traditional web application firewalls since the exploit hides in the response, not the request. Affected surfaces include web chat UIs, email summaries, dashboards, and mobile web views. In other words, any interface that renders model output in the browser is at risk. When improper output is rendered unchecked, it manifests as cross-site scripting, XSS. Let's explore 4 ways it surfaces. First is reflected XSS, where the attacker's malicious prompt is immediately echoed back and executed. Next is stored XSS, a persistent threat where malicious content is saved in a database and later executed whenever other users view it. DOM-based XSS arises when the client-side code takes the model's output and dangerously syncs it into the DOM. Finally, special cases, obfuscated vectors, markdown injection, or SVG rendering bypass standard filters with disguised payloads. In each case, the common mistake is assuming the model's text is harmless. Up to this point, we've dissected individual XSS flavors. But how does a single malicious response cascade into full compromise? To answer that, let's break down the vulnerability chain. It starts with the model's output. The attacker influences the LLM either by injecting a malicious prompt or by leveraging poisoned retrieval augmented data. Next, your application naively renders this output, perhaps by inserting it straight into the DOM via inner HTML. The browser then interprets the content, spotting script tags and event handlers, and treating them as executable code. Finally, the payload executes, running in the victim's session, stealing cookies, or performing unauthorized actions. The critical takeaway is that input filtering alone isn't enough. You must validate and sanitize output, because the model itself acts as an unverified proxy that can construct complex payloads. Understanding this chain helps you see why every link, from influence to execution, must be secured. Now imagine you're an attacker. You don't need to breach the server, you just need to get the model to echo your script into a chat history. The attack starts with recon, mapping targets like chat UIs, email previews, and dashboard widgets. Then comes crafting payloads, SVG onload events, hidden iframes, data URI schemes, and polyglot payloads. The attacker works to bypass filters by exploiting markdown, double encoding, and obfuscation. Once they land their malicious output, the victim's browser renders it, and the script executes via vulnerable inner HTML syncs. The attacker then causes impact, session hijacking, CSRF actions, DOM defacement, and key logging. They exfiltrate data by sending cookies, dumping local storage, capturing screenshots, and even scraping the clipboard. Finally, they persist, storing the payload in databases to infect more users over time. Trusting model output without checks makes every step frighteningly easy. What kinds of payloads do attackers coax LLMs into generating? One technique is event handler injection, embedding attributes like onError or onload in tags so the browser executes malicious code on image load. Another involves JavaScript protocols. The model may be asked to produce a helpful link, but that link's href starts with JavaScript and executes hidden code when clicked. Attackers also abuse markdown exploitation. They instruct the model to create a markdown link that auto-converts into an HTML anchor, enabling XSS. Finally, there's obfuscation and polyglots. Base64 encoded iframes or CSS injections that look benign to filters but become executable when interpreted. The diversity and subtlety of these techniques underscore why output must be rigorously sanitized. How do we neutralize these threats? The first line of defense is context-aware encoding. When inserting LLM output into HTML, convert dangerous characters into their corresponding entities. In attributes, encode all non-alphanumeric characters, and within URLs, encode parameters. When rich text is unavoidable, run it through a sanitizer like DOM Purify, which strips out dangerous tags and attributes. On top of that, enforce content security policy headers, restrict script sources, and block inline scripts to mitigate residual risks. Use frameworks that auto-escape content instead of manually setting inner HTML. Avoid dangerously set inner hfiction and default to safe rendering. Together, encoding, sanitization, and CSP form a triple layer of defense. Let's put these principles into context. A customer support chatbot allowed rich HTML in its responses. Developers rendered the model's output directly into the DOM via inner HTML. An attacker injected a malicious SVG element with an onload handler. When a customer later viewed the chat, the browser executed the embedded script, hijacking their session. The key lessons? Trust no output. LLMs mimic their training data, including attack payloads. Use safe rendering functions or frameworks like React's text content rather than raw HTML injection. And if you must support rich formatting, run the response through a strict sanitizer first. Remember, the model is not a sanitizer, it's a text generator. Improper output handling isn't just a technical curiosity, it's a business nightmare. Financially, it triggers expensive incident response, regulatory fines, and lost revenue from downtime. Legally, privacy regulations like GDPR and CCPA can lead to lawsuits and breach notification obligations. Your brand suffers when screenshots of AI-driven hacks go viral. Trust evaporates, customers churn, and media coverage turns sour. Operationally, teams scramble through emergency patching, system downtime, and resource diversion. Worse, AI-generated excesses can self-propagate if the model learns from poisoned output, an AI worm. And because users trust AI responses more than random web content, the damage feels like a systemic failure, not a bug. To fortify your applications, implement safe rendering patterns. In a React example, avoid dangerously set in the N and simply insert the content as plain text. This ensures auto-escaping. On the server side, define a content security policy that restricts scripts to trusted sources and blocks inline scripts. When using Markdown libraries like mark.js, enable sanitization and disable features that automatically create links. Remember this pro tip: never rely on regular expressions to strip HTML. Browsers are forgiving and will still execute malformed code. Use context-specific encoding functions for HTML, attributes, and JavaScript, default to plaintext whenever possible, enforce a strict CSP, and disable auto-linking to prevent JavaScript abuse. The next layer is browser hardening. Eliminate dangerous things like inner HTML, outer HTML, and views VHTML. Prefer inner text, text content, or safe Markdown components that treat output as text. If you must render rich HTML, isolate it inside a sandboxed iframe, so any script executes in a confined environment without access to cookies or local storage. Defense layering is key. Sanitization removes most threats, while hardening limits the damage when something slips through. Use battle-tested libraries like DOM Purify with strict tag and attribute whitelist, and leverage trusted types to restrict dangerous assignments to inner HTML. The combination of these measures dramatically reduces excess risk. Secure output handling isn't only about the front end. At the system level, schema enforcement ensures the model's response conforms to an expected structure and rejects unexpected fields. Implement safety middleware that post-processes every token stream. Redact personal data, strip dangerous tags, and scan URLs against threat intelligence. Use policy prompts that instruct the model not to generate HTML, JavaScript, or SVG, or to wrap code in fenced code blocks. And finally, invest in observability and logging. Detect patterns like onError equal to or large base64 strings and trigger alerts when suspicious output appears. By embedding security into the pipeline, you prevent malicious content from reaching the client in the first place. Improving security is a journey. So here's a practical roadmap. In the first 30 days, remediate immediately. Replace dangerous syncs with safe renderers. Deploy a strict CSP with nonces. Integrate DOM Purify for all output and disable auto-linking and risky Markdown features. Over 60 days, harden the system. Enforce trusted types, implement strict JSON schema validation. Enable detailed logging of suspicious render patterns and isolate rich text in sandboxed iframes. Within 90 days, aim for strategic assurance. Conduct red team exercises targeting output pipelines. Build dedicated microservices for safe HTML rendering. Integrate automated XSS scanning in your CI/CD and establish secure coding guidelines for AI interfaces. A crucial implementation note: apply these controls at the API gateway or backend. Do not rely solely on client-side validation. As we conclude, remember these key lessons. Untrusted output. Treat any language model response exactly like user input, tainted and dangerous. The vulnerability isn't in the model's generation, but in the browser's rendering, so never dump LLM output into inner HTML. Adopt defense in depth. combine context-aware encoding, sanitization, and strict CSP, and build safe pipelines by enforcing schemas and using middleware to strip dangerous tags before they reach the front end. Designing security into your AI infrastructure isn't optional, it's essential. In our next episode, we'll explore system prompt leakage and control bypass, how attackers reverse engineer hidden prompts to circumvent guardrails. Until then, revisit episode 1 if you missed it. Implement the defenses we covered today and stay vigilant. Your users' trust depends on it. So before you go, hit like, drop a comment with your thoughts, and subscribe to the channel. Turn on notifications so you're the first to catch episode 3 as soon as it drops. Thanks for watching, stay curious, stay secure, and I'll see you in the next episode.